this video, we'll be discussing power analysis, a little bit about what does that even mean and how do we go about doing it and some of the factors that play a role in its calculation. So you can check some of the details out in section 3.7 of your book. Often we wish to determine what sample size is required for an experiment, and this is called a power analysis. Now this seems kind of weird because power is the probability that we don't miss something, in a sense, not committing a type 2 error. But we call it a power analysis when we're calculating the sample size. Now, why this is called a power analysis is because we're usually determining the sample size necessary to achieve a certain power given other things. Now, this answer depends on a lot, including what type of experiment you're doing, how it's going to be conducted, the resources, the desired sensitivity, which just refers to the difference in means that you want to be able to detect. But as a general rule, increasing your sample size, increasing the number of replications, increases the sensitivity or the size of the difference you can detect, and it makes it easier to detect things of a fixed size. So you're more likely to detect things if the size were the same. Now, one thing about power analyses is it really is best to conduct a power analysis after having done a pilot study. And this is important because as we're trying to determine what sample size is necessary, we have to make some assumptions about what's going to happen in the study, because the sample size that's necessary to detect a really, really small difference is different than the sample size that's necessary to detect a really, really large difference. And how do I know which type of difference I'm going to have? Well, honestly, you don't. So a power analysis, or excuse me, a pilot study is going to give you a lot of really good information about what to realistically expect in your experiment and let you get real estimates for the other variables that are necessary for the calculation of the power analysis. Now you can do this in a variety of different softwares. I like the software G-Power, but can't always get it on the school computers. You can definitely do it in R. There's a package called PWR that you can do a power analysis in. You can also do it via simulation, where you construct a simulation, and I think we talk about that in our advanced data analysis class, where you design power analysis simulations. Actually, that's a really good way to do it because simulation is the only way to do complex cases. Built-in software can do simple cases, a t-test and ANOVA, but as you get to more complex cases and analyses, software can't actually do that. You kind of have to construct your own simulation using a whole ton of different assumed values. And again, if you have to make all of those up, there's a decent chance that you're going to make a mistake. And that's where a pilot study is so important, because that way you don't have to make up all those numbers. You run the pilot study, you get at least a rough guesstimate as to what those numbers will be, and then you can run the analysis to make a much more accurate determination as to what the sample size likely is to achieve a certain power. Now, there are a variety of different components that come into power. The first is the type 1 error rate, or that nominal alpha level that we have. The second is the type 2 error rate, which is the type 1 error rate's probability of falsely rejecting the null hypothesis. And when we get to the type 2 error rate, we're looking at the probability of falsely rejecting the alternative hypothesis. So the power is 1 minus the type 2 error rate, and it's the probability of not falsely rejecting, so accurately getting the type 2, accurately getting the alternative hypothesis. The sample size n is a component that's related. And then there's two last components: the size of the difference between the groups. Let's say we're looking at group means. How far are the part of the group means? Are they pretty close together? We've got one here and they're like real close together. Are they pretty far apart? Or are they like a whole screen apart? What's the size of that difference? And then, of course, what's the variability within those groups? I have a little asterisk on here because these are often lumped together into the term effect size. The size and variability, we tend to have these standard measures of effect size that kind of lump together size and variability. Now, on the previous slide, we talked about sensitivity. Sensitivity is the ability to detect smaller effect sizes. So the effect size that's how the effect size is related to sensitivity, and that's where kind of sensitivity falls on here. Sensitivity is talking about the size of the effect that we can detect. More sensitive tests can detect smaller effect sizes. So again, I was talking about what the type 1 and type 2 error rates mean, and that's kind of a tough thing to see. So here's a table that can hopefully help. We've got reality, and then we've got true rejection and false rejection, and then we've got the measured or perceived decision. So true and false. So this is what's going on in the back end, and this is kind of like our statistical decision. So let's say we reject the null hypothesis, and we should have. Well, that's a correct decision. We reject the null hypothesis. That's our decision, our statistical decision, and we should have in reality. That's a good thing. But let's say we fail to reject the null hypothesis, and we actually should have rejected the null hypothesis. Well, in that case, we said there is no difference, but in reality, there actually was a difference. So that's the type 2 error, is there was something there and we didn't see it, and that's a bad thing. And then, of course, on the other side, let's say we fail to reject the null hypothesis, and we should have failed to reject the null hypothesis. That's a good thing. But we could also reject the null hypothesis, and we shouldn't have rejected the null hypothesis. And that's a type 1 error when we falsely reject the null hypothesis. Our statistical test said, yes, there was a difference between the groups, or yes, the treatment was effective or something, but it really shouldn't have said that. Now, this can be really tough to think about. So what I like to do is really think about this like a court case. So rejecting the null hypothesis is like a declaration of guilt. So actually, you can draw this out on your notes. You write guilty instead of true, and then false is not guilty. So we've got guilty instead of true and not guilty. And then we've got measured or perceived. So this is like what the jury says. This is what the jury says. This is what our statistics say, and that's analogous in the court case to what a jury says. And then reality is like, did you actually commit the crime or not? So if the jury says guilty and you were actually committed the crime, then that's a good thing. The bad people go to jail. If the jury says not guilty and you didn't actually commit a crime, then that's a good thing. You didn't commit a crime and you didn't go to jail, so that's a really good thing. If you committed a crime, but the jury says not guilty, then you let a guilty person go free, and that's a bad thing. And if in reality you didn't commit a crime, but the jury says guilty, then that's a bad thing. You just put an innocent person in prison. So typically what we control in this analogy is the probability that we put an innocent person in prison. That's what our alpha level is. And then we try to minimize as much as possible, given a fixed level of alpha, how many innocent people are you willing to put in prison. Then we try to reduce as much as possible the guilty people that we set free. And again, guilty people that we set free sounds bad, but in our research scenario, there was a real cool treatment effect that was going on, and we said that there wasn't anything going on. So this can be really, really annoying when you're researching a particular effect, and the effect that you were trying to study and look for actually was there, but your statistics said it wasn't there. That type 2 error can be a pretty sad thing to happen. So both of these are bad things. But I really like the court case analogy for a couple of reasons. First, a court case, just like in statistics, you have this assumption of innocent until proven guilty. So you're going to be innocent until you're proven guilty in this court case, and that's a good thing. You want to be innocent until proven guilty. But just like in statistics we go with the null hypothesis until we have evidence to go with the alternative hypothesis. So innocent until proven guilty is a great analogy towards what we do in statistics, which is null hypothesis until proven to be the alternative hypothesis beyond a reasonable doubt. So that's a good thing. And again, the idea that we have a statistical test, but that it's not always in line with reality, that the jury decision could be wrong. That's a good analogy. And then actually, a whole ton falls into place here because things like sample size actually fall into place. How many replications do you have? Replications, the number of replications in is like the amount of evidence in the case. When I have more replications, we have lower error rates, all other things being the same. So if I have a lot more evidence in the case, then the probability that I make an error is lower. And the effect size from the components in the previous slide, the effect size is also part of this. The effect size is kind of like the quality of the evidence. So I might have less evidence, but if it's of a really, really high quality, then the quality of the evidence also lets me make less errors, all other things being the same. So all of these different components actually play really well for me in the analogy of a court case, and it makes it really nice to think about what we're talking about here. And so in statistical power, the idea is that we want to, with statistical power, correctly convict the guilty people. Or again, in a research setting, we're trying to find treatments when they're actually effective. Now, as the components change, like the type 1 error rate, the type 2 error rate, the sample size, the size of the effect, they impact each other. And we can look at how one impacts the other by holding all the others equal. So for instance, when the type 1 error rate increases, the probability that we find a true effect also increases, all other things being held equal. Consider what the meaning of this is in the court case scenario. If the type 1, this is like having a judge who just declares more people guilty. Well, the type 1 error rate, that's the probability that an innocent person went to jail. Well, if you have a judge who just starts sending more people to jail, well, you're going to increase the probability that innocent people go to jail, but you're also going to increase the probability that guilty people go to jail. So as your type 1 error rate increases, your power also increases, all other things being held equal. And that court case scenario kind of makes sense. Again, if you have a judge who just sends more people to jail, the innocent go to jail and the guilty go to jail. So these increase together. Now, again, power analysis is primarily about how things interact with sample size. So let's look at how sample size impacts some of these other components. And again, for all these, you have to assume that the components are all the other components are held constant. So as sample size increases, as we have more data, the power increases. And another way to say that is that the type 2 error decreases. So as we have more data or more evidence, we are more likely to convict guilty people or more likely to find a true effect when it's there. As the sample size increases, alpha, the level of type 1 error, decreases. So we're less likely to falsely convict innocent people. As the sample size increases, the detectable effect size decreases. So that is the sensitivity increases. So as our sample size increases, we're able to detect smaller and smaller and smaller differences between groups. And this is kind of nice to increase that sensitivity. And one of the reasons often people want to increase the sample size is so that their tests can become more sensitive and they can detect smaller differences. Now, this wasn't in my notes to talk about, but I will mention it here anyway, that actually this can be a problem. The fact that the sample size increases makes the detectable effect smaller and smaller, so we can detect smaller, more subtle effects. Sometimes that's a bad thing. Why is that a bad thing? Well, let's say that I have a huge sample size, and this is happening in modern data where I have millions or even billions of observations. Well, the sizes of effects I can detect are really almost non-existent. Like on a graph, I would never be able to see the difference between two things, but I can detect a difference in it because my sample size is so massive. That's a problem that we call being overpowered. And there's some different things that we can do there, but we want to be careful as our sample size gets really, really large, because we can start to detect effect sizes that are so small they're no longer practically meaningful. Actually, this is part of our conclusions too, where we don't just talk about statistical significance, but we talk about the practical effect. And as long as you do that, actually the sample size being too large isn't an issue, because you have both the conclusion of statistical significance, but then also discussion of the practical effect. So even if you're analysis detected a minuscule effect size, in your discussion of the practical effect of what you saw, you can elaborate that the practical effect was really too small to be meaningful. So how do we select these different parameters? Well, alpha and beta are typically selected by the researcher ahead of time, so a priori. Typical values for alpha are alpha equals 0.05. Typical values for beta are beta equals 0.95 for a really, really high-powered study, or 0 equals 0.8, which is much more typical and is probably the typical level that people use. The last one that you have to pick, so there's 4 elements: sample size, alpha, beta, and effect size. And recall beta and power are the same. So sample size, alpha, power, and effect size, set it a slightly different way. So if I'm trying to determine sample size, I need alpha, beta, and effect size, or alpha, power, and effect size. Effect size. How do you determine effect size? It's a guess at the end of the day. And ideally, what you're going to do is you're going to run a pilot study and see what the size of the effect was with just a few trials in your study. And then that gives you a really good guess as to what the effect size would be. Sometimes you can use previous research if a similar study was done to see what the size of the effect is going to be. But honestly, picking the effect size is a really important component of this, and it's a component that I'll say is not always done as meaningfully as it should be done, and that can be a problem. I should mention, I think I mentioned earlier, we said beta of 0.95 or 0.8. Those were power values. The betas for those would be 0.05, just like alpha, or 0.2. And a beta of 0.2, which matches with a power of 0.8, that is what we typically input for that beta or power parameter. The type 3 error. The error of having solved the wrong problem. If you ask the wrong question, you can still make an error. There are many errors that relate to the fact that you were looking at the completely wrong question in the first place. Type 3 error is a bit tongue-in-cheek. There are a variety of different people who have these types of errors: type 3 error, type 4 error, type 5 error. Honestly, these aren't really agreed on. These are a bit in fun, again, tongue-in-cheek. But the problem is very real, that sometimes you ask the wrong question or you solved the wrong problem. And this is kind of similar to model fit, where we assume that you're including all the right variables. And if you're not including all the right variables, then you can have done the whole analysis and really walked away with absolutely nothing because you looked at the darn wrong variables. Again, the moniker type 3 error is a bit of a misnomer because there's not really wide agreement on what a type 3 error is. It's something that somebody said, hey, this is an error, and we've got type 1 error, which is, falsely assuming that falsely rejecting the null hypothesis. We've got a type 2 error, which is falsely failing to reject the null hypothesis. And then we got a type 3 error, which is it didn't really matter what you did with the null hypothesis because you asked the wrong question anyway. And so, again, some consider different concepts to be a type 3 error. So the name is not particularly standard, but there is wide agreement on the principle. And I include this as just a bit of fun. Because it's kind of interesting. These authors actually also have a type 4 error, which is deliberately having written a deceptive problem, where I write a problem and then solve it, and it sounds really good, but maybe it's written deceptively. All right, well, to close out this chapter, we're going to talk about just a couple of advanced details, and we're going to kind of cruise through these. So the first one is maximum likelihood. Now, you probably talk about this in your math stats course, but the likelihood function is really just a joint PDF of all the different observations, where the observations are fixed and the parameters are unknown. So this is our likelihood function. And really what we're doing is we're just maximizing this likelihood and picking parameters that make this function the biggest. So literally all we do is we take the max of this with respect to the parameters, and whatever those parameters are, those are the maximum likelihood parameters. Now I include this because for the variance components, this is the method of estimation that our textbook recommends. Now maximum likelihood, the other estimation style is least squares. Honestly, these both work fine. Maximum likelihood is a much broader style and is much more applicable in areas where least squares isn't necessarily. So it's applicable to a broader set of conditions and cases. But under a few assumptions, maximum likelihood and the ordinary least squares method actually give the exact same result. So it really doesn't matter what you choose. But just be aware that when we talk about maximum likelihood, what we're talking about is writing the likelihood function, which is the joint PDF of all the observations. And then we literally just pick whichever parameter makes that the biggest. So we maximize the likelihood. Now when we're looking at the variance components, the residual maximum likelihood is an iterative way that you can look at the estimation of the variance components. And the point estimates from the residual maximum likelihood will agree with the moment estimates. I guess it kind of depends on if the design is balanced or not. But what you'll see sometimes is that the confidence intervals that come out from this iterative procedure aren't always theoretically correct. And I think we talked in an earlier lecture about how sometimes it's kind of embarrassing when you have a negative confidence interval that comes out for a variance component, which indicates the an impossible potentially solution. So do be aware that can happen here. But the residual maximum likelihood is another estimation method that we can use. And as completely as an aside for JMP, I'm just going to point out, we talked about the intra-class correlation coefficient. This percent of total is what you can use for that calculation. Again, you see close to 80% was explained by the variable in that one situation. This is actually the same problem. All right, the last kind of advanced detail that we're going to talk about before being done for today is the regression model. So in the regression model, this is just a different way of approaching when we have our independent variable, which is a continuous variable that has been categorized. So previously what we've been saying is if it's a continuous variable, you break it down into different categories because it's experimental design and you want replications within each of the levels of the factor. And that works, and it works fine. But what we haven't talked about is that you don't have to completely categorize that variable. In fact, you can still maintain the relationships between the different levels. So for those of you who've taken regression, this should probably make sense. And in fact, a lot of this is probably review. But we can use a regression framework to account for the relationships between these. Now you can use a linear framework, but you can also use the quadratic framework or any level of polynomial. I mean, you can use all of your regression tricks for modeling these different things. Now note that you're going to have a limit of the range of values within your x or independent variables, because again, they're fixed at these different levels for the experimental design purpose, but you can account for the nature of the difference in the fact that we do have a continuous variable with interval or ratio level measurement and use that. This could be handy if you wanted to extrapolate to other potential levels that may fall in between, but we have to be really careful because you do have to make a fair amount of assumptions to do such an extrapolation. If we wanted to build on this and start adding other things, let's say we're looking to optimize a particular design, we could use this type of model to then guess, okay, what should our next experiment be? And that goes into something called a response surface design, which is discussed in the text. So this has been our last video for Chapter 3, where we really discussed the one-way ANOVA and some of the designs that can come out of that, including the fixed effects ANOVA, random effects ANOVA, and then a whole slew of sides that come with that and the different concepts that come with those different analyses.